We would like to, of course, everybody would like to better understand the hadron structure, even people from nuclear physics and particle physics. And it's a pleasure to have Dr. Ragoni here from Creighton University. He's a member of the ALICE Collaboration. I'll be helping here. If somebody wants to ask a question in Portuguese, I can translate the question for the speaker. And you have about 50 minutes to present your results, and then we can go to a round of questions. Let me ask you, do you prefer the questions to be asked during the presentation or only in the end?
Just stop me. It's something for the students. So in the end, if they have questions, feel free to stop me anytime.
Ok. So I'll present you also em português now. Então hoje a gente tem o Dr. Simone Ragoni, que vai falar para a gente sobre a estrutura dos hadrons. Isso interessa o pessoal de física de partículas, física nuclear. E eu perguntei para ele, se alguém tiver perguntas, pode perguntar durante a apresentação. Se quiser colocar a pergunta no bate-papo, eu também posso ler a pergunta. E se quiser perguntar em português, eu posso traduzir para o inglês a pergunta para facilitar a interação. E ele é um membro, a gente tem o prazer de ter ele aqui, que ele é um membro da colaboração ALICE, que é um dos experimentos do LHC. Okay, so I think we should start, please.
Yeah, I understand that I should speak very slowly, right? It's preferable.
Yes, clearly and slowly.
Okay, hi everyone. I'm slightly older than you are. I'm a postdoc at ALICE. Since 2 years ago, I did my PhD also in ALICE. In the United Kingdom, so I simply stayed around for a while longer after the end of my PhD, hopefully really a while longer. Essentially today I want to give you an introduction to the physics that we do in ALICE, and also the physics that I'm mainly involved with, which is these ones. It's a very nice name, UPCs, ultra-peripheral collisions, and I will be talking about it later. To be honest, I feel like this field of research is kind of the most reasonable field of research in ALICE, so it's good luck for the first exposure to the experiment. So firstly, I need to give you a brief introduction to ALICE and our mainstream physics program. Because actually the UPC group is a very small fraction of the experiment. So ALICE is a big collaboration of about 1,200 people, and only about 20 people are involved in this specific UPC program, while the rest of them are involved in the mainstream physics program of ALICE. So the main idea is that the ALICE detector, which is this huge box, whoops, too fast. Let's see, let's see again, does it go? Yeah, which is this big box here, studies the primordial matter, essentially studies the matter in all its states, if you want. So so as you know, we have a solid, liquid, and vapor, and then plasma, which is essentially the state where they're all ionized. And actually, the main goal is that matter can transform. This is very outreach style slides. Actually, the first few slides that we see here, I stole them from the outreach talks, from the visual material for outreach in ALICE. And essentially, you normally study this kind of a diagram for when you go from solid to liquid to vapor. And in particle physics, because this is actually high energy nuclear physics in ALICE, we do something similar. So we study the universe as a function of temperature and net baryon density. And this diagram, which you might see for the first time, shows that essentially there are a few main regions here. You have the standard hadrons. Then here is the nucleus, if you want. If you go through this axis, you go towards the neutron star. This part here contains essentially the quarks-gluon plasma. And essentially in colliders, so in particle accelerator, we put ourselves at a net baryon density 0, and we go at very high temperatures. So we go along this axis towards something like here. And essentially, we study exactly the existence of something called the quark and gluon plasma, which is actually what happened at the beginning of the universe. So what we know about matter, apart from the very nice animation that I don't know how to do by myself, but we know that matter is mainly made by vacuum, it's material. We have 4 forces, 4 elementary particles constitute ordinary matter. So you have up, down, electrons, and neutrinos. Muons, if you want, that hit all of us at any moment. And then we know that the existence of a plasma of quarks and gluons. This is the main idea. So how do we recreate this original state of matter? We take 2 lead nuclei, we accelerate them pretty much at the speed of light. We collide them, and then magic happens. We have a blob in here of super dense matter, which is the quark-gluon plasma. Then the fireball expands. You have stuff coming out of it. We take this stuff, we analyze it, and then we say, okay, we found a quark and gluon plasma. The idea here is very simple. You can imagine the quark and gluon plasma essentially as a blob of super dense soft chocolate, and then the particles coming out of it are kind of the hardened chocolate that comes out of it. So essentially, we use the particles coming out of it as kind of a thermometer, if you want. And so we study, for example, G psi, upsilon, all these resonances, which have a certain kind of binding energy. So essentially, by studying the presence or not of these these resonances like J psi and upsilon, many harmonia, we kind of understand the temperature of the quark-gluon plasma inside. So this was just to give you an idea. And then sometimes we say that actually what we are doing is that we have the Big Bang, which has this kind of evolution from QGP to cosmic microwave. And then we have small Big Bangs that we make every time in the lab at CERN. This is the connection essentially to the cosmology, but the connection is very loose. So it's a very kind of weak connection between the Big Bang and the micro Big Bang that we normally have at the ALICE or in ALICE. So this is essentially how our detector looks like when we have particles inside of it. So you see essentially quite a few tracks. So these are all particles produced in the event. You see that there is a huge mess here. So reconstruction of all these tracks, so essentially joining the points left by each particle inside of the layer is a very tough job. What I want to say is that the difference is that in ALICE, in something that we call central event, we have about 20,000 particles generated in the entirety of the solid angle, if you want, of the collision. While normally in a typical high energy collision event, so for example, proton-proton interaction, proton-proton event collision in ATLAS, CMS, other experiments, you have something of the order of 100 particles, if you want. So we're talking about a lot more particles than normally you'd have to deal with. And also for me, this is unusual because, as I will be talking about, I do something which is essentially the complete opposite of all of it. So instead of looking at 2,000 particles per event, I look just at 2 particles produced in an event. So this is kind of the magic of a type of physics called diffractive physics. So essentially, if you want to say there is a particle collider coming up in US, which is called the EIC, electron-ion collider, which will be an electron-ion exactly collider. And our ultra-peripheral collision program is complementary to the main ALICE program, and it is really the forerunner to the EIC activities. Essentially, we are anticipating what will be done at the EIC in about 10 years. So essentially, what I will be showing you is first what exactly I am doing in terms of theory, if you want, the ALICE detector, how it looks like, what I use normally to perform a measurement. Then the results on something we call the exclusive and dissociative GSI IP-led UPC, and the results on coherent GSI and UPC-led, and then essentially the measurements of the energy dependence of the photonuclear cross-sections. So these are very big words, but we'll go through them with quite some detail. So if you are lost, stop me. Ask me questions and I will repeat it or explain a bit better. So first, the introduction. As I was saying, in my opinion at least, UPCs, ultra-peripheral collisions, are the most reasonable type of physics that we have in ALICE, and also the more interesting. It's not only because I've been doing it for about 6 years now, but also because it's quite interesting. This is the main diagram. You have lead ions, lead. You have a photon on one vertex, which interacts with a colorless object on the other side. This is sometimes referred to in literature as a pomeron, but you can think of it as a system of 2 or more gluons. In fact, most frequently you see this as a gluon ladder. You have that the photon converts in a quark-diquark pair. So quark-diquark. It interacts with the pomeron from the target, and it is essentially fixes it in a state of a vector meson. So you have a GSI, psi prime, rho. You can have a phi. What's the limit? The limit is that you have to have the same quantum numbers of the photon. So the photon, if you remember your master classes, as a JPC of 1 minus minus. So all the particles that come out of this process have to have a JPC of 1 minus minus. And this essentially brings it to just about psi, psi prime, rho, upsilon, essentially all the charmonium, the bothonium, and like that. By the term ultra-peripheral collisions, we mean, in fact, all these events which feature a large impact parameter which is beyond the reach of the strong interaction. This means that essentially the sketch that you saw before of the two lead ions colliding against each other and generating QGP, this is not possible. So essentially, these are very far away from each other, so they just interact through an exchange of a photon. What's nice about this type of process is the fact that the cross-section of this process is dependent on just the gluon distribution squared. So you see here xg squared. This is a result that has been known for 30 years. And as far as this type of physics is concerned, we typically differentiate between coherent and incoherent photoproduction. Because this type of process, when you have a photon which is interacting with the pomeron, is normally called photoproduction. If you think that this is a lead nucleus, then the photon can couple with the nucleus coherently. It means that it interacts with the entire nucleus, and this yields coherent photoproduction. In the other case, instead, you have the photon interacts with a single nucleon of the target of the nucleus only. And this means that we are referring to incoherent photoproduction. Obviously, since it is impacting a single nucleon, it means that the nucleus itself is excited, is an excited state, and then the nucleus can dissociate. Okay, so it is emitting a nucleon in the case of incoherent photoproduction. Normally, when we are in the field of high energy physics, particle physics, there are a few variables which are important. One is the PT, so the transverse momentum of the particle, if you want. And here I say that the two processes, coherent and incoherent photoproduction, feature very different average PTs of the vector mesons for the two processes. The reason is very simple. So if you think about it in terms of uncertainty principle, not uncertainty, what's the name in English? Indetermination principle, I think. So it's essentially the PT is roughly of the order of, goes as 1 over the radius of the target. So if you think about it, in the case of coherent photoproduction, you are coupling with the entire nucleus, which is a lead nucleus. So essentially, the size of the target is about 7 Fermi. Whereas in incoherent photoproduction, we are coupled with a single nucleon, so 1 Fermi. So normally, you would expect something of the order of 1 over 7. Okay, 1/7 for the average PTs of the two processes. And then here essentially I say the two main variables. One is T, which is essentially the square of the momentum transfer between the momentum ongoing target nucleus. If you want, you can think of it as kind of the deviation of the targeted nucleus, if you want it. And W, which is essentially the energy of the photon target system. If you want, you can think of it as a photon and the lead nucleus. The reason why we do all this effort to publish papers is that here you see a scheme essentially of the process. So you have the two lead nucleus like here. So with their own electromagnetic fields, and then you have that they each come with their radii, and then the impact parameters, so essentially how close they get to each other, is larger than the sum of the two nuclear radii. And the reason for doing all of this is that there are two, actually. One is that we look for a gluon saturation. So if you remember studying about PDFs during university, then you have the gluon and the quark distribution. So the quark distribution for U and D, they look like this. However, in the case of the gluons, we just see them increasing all the time, okay? And there is a lot of uncertainty here. These are data from H1 in ZEUS, which are old experiments at here. It's a previous collider here in Europe, which is now not functioning anymore. But then, if you think about it in terms of PDFs, this has to be normalized to 1 afterwards. So essentially, we expect that this actually, at a certain point, will be tamed. So it will have to do some kind of hoop like this and then go to 0. This is what it means to look for Gluon saturation. Essentially, we are looking for the point where the PDF is going down. Spoiler. For now, it seems like just rising, so no Gluon saturation hint for now. The other thing that we look for is nuclear shadowing. Essentially, you have that the PDFs in the nuclei, they're different from the PDFs for single protons or neutrons. If you want, we study something called nuclear shadowing, exactly, which is essentially the fraction of the gluons in the nuclei divided by the number of nuclei times the proton gluon PDF. And for now, this looks like here. So this is one of the most recent computations. And you see it has this kind of structure, and there are large uncertainties in this part here. Essentially, you cannot really say anything at this point here. However, with our data, we show that we can say something about the nuclear shadowing. So essentially, the fact that this is less than 1 at very small x. So essentially, the x here goes like this, and we're looking towards this part here. Smaller x means higher energies. Again, if it's not clear, please stop me, and because it might even get more confusing. So, concerning the ALICE detector, this is how it looks like. So, this is essentially the scale of the human. So, this is a big box of about 16 square meters, 16 square meters, and 25 in total. So it's very long, it's very large, and it is usually separated, as you see here, in 2 parts. So the first part, which is put together inside of this red box here, which is the magnet, and the other, which is the forward muon spectrometer, which is this part here. Here there is a gray part, which is a big absorber. So essentially, it's a huge chunk of cement, lead, and other things. And essentially, what it does is that it stops particles. So then, at the end, here you only see the muons coming out of there. And there are essentially a few types of measurements that we perform. So we can look for a forward GPSI, so essentially GPSI which is produced in this direction. So we have 2 muons here. You can have a GPSI produced in the central barrel. So you looked for a lepton pair here. And then nothing else. So this is the entirety of that ALICE is able to see. So when you have a UPC event, the ALICE detector is completely empty, apart from 2 particles here, which is quite different compared to the huge mess that you saw in the beginning when you had 2,000 particles or more. Another type of configuration is this one. So when you have 1 muon in the central barrel and 1 muon in the forward muon spectrometer. But this is a very difficult configuration because it means that you have to, what we say in jargon, read out the entirety of ALICE in a single time. So it's very tough to actually measure this type of process when you have 1 muon in the forward spectrometer and 1 muon in the central barrel. So then the results on exclusive and dissociative GSI in P-led UPC, so which brings together a bit the theory that you saw and my few words on ALICE. So here we look just for the GSI, so there is just the GSI in the entirety of ALICE in a P-led event. So essentially you have a proton beam and a lead beam going against each other. In this, then essentially the rapidity of the particle, which is, if you want, you can think of it as something that is a bit more complicated than actually the direction of the particle, but just a tiny bit more complicated than that, is a proxy for the Bjorken-x of the process. Okay. Where Bjorken-x is essentially the momentum fraction of the parton that you are hitting. If we take ALICE data, where we consider essentially where we can measure our muons and our GSI, this means that we can bring down and study the gluon PDFs down at level 10 to the minus 5 with ALICE data. So this is essentially how it looks like. So you have the cross section for GSI as a function of the energy. So this is at the scale of a TeV. And you see essentially how the data look like. And you see, in fact, that the data stand on a power law line. So essentially, here is a log scale, here is log scale, and the shocking, this is a power law. So there is a power law growth of the cross sections, which doesn't change throughout the energy. This means, if you remember, the cross section relates to the gluon PDF squared. This means that there is a power law growth of the gluon distributions down to 10 to the minus 6. It means that nothing changed from here until here. So there is no clear signs of gluon saturation. Yes, another thing is that in this type of events, you have that the lead ion is the source for the photon always, because if you think about it, a lead ion has a Z number of 208, whereas a proton only has 1. So basically, essentially, you are comparing a I don't know, a flashlight with a USB light. It's if you want, it's this is much stronger. And so essentially the entirety of the photon source is entirely driven by the presence of the lead ion. And in the same measurement, we also managed to measure for the first time something that we call dissociative GSI. What does it mean? It means that actually the proton was excited. You see here a star, and for the fraction of the ratio of the cross section, so between in the case when it was exciting and when it wasn't, and this looks like this. The reason for doing it is that if we invert the beam configuration, so instead of doing P lead, we do lead P, then we can access the very high energy part here. And there are two lines in this case. So there are two models. One is this Mantisari model, and the other is this Contreras-Sepila-Takaki model here. The differences between these two is the presence or not of gluon saturation effects. So essentially, in this case, there is gluon saturation in there. In this case, there isn't. So essentially, if when we go and measure lead P instead of P lead, we see that the cross section here stands about here instead of here. This is a sign for the presence of gluon saturation effects. So this brings me to coherent and incoherent GSI instead of in UPC lead. And this is essentially how our things look like. So this is the GSI, it stands at 3.1, and you see it's very clean. So having this type of plots where it's all super clean is something that is very unusual in a machine like ALICE, which is a hadron collider, because you have all this remaining QCD stuff happening inside. And so this is kind of a unique opportunity that UPC physics gives you. So you have a very clean signal here, and you see there is even something here which is a psi prime. And you have something here which is usually a background. In other types of measurements, having this kind of line here would hint to some kind of combinatorial background. Whereas in the case of UPCs, this continuum here, so this background here, is again a physics process. It's nothing more than photon-photon in leptons. So essentially, the unique opportunity that UPCs grant you is the fact that in a single invariant mass distribution, you're really looking at the 3 different signals. So gamma-gamma in leptons, J-psi in leptons, M psi prime here. And if we take this data here, so between 3 and 3.2, we go and look at the PT distribution. This is how it looks like. So there is big peak here, and then it falls. And you can see that the peak is entirely essentially driven by this blue line, which is nothing more than coherent J-psi. And then you have incoherent J-psi, which is here and here. And if you compare the mean of the 2 distribution, coherent J-psi, which is here, the mean should be about 0.07, so somewhere here, 0.01. If you go to the incoherent, this is the mean is somewhere shifted, so it's about 0.5, more or less, 0.4, 0.5. And you see immediately that what I was saying in the beginning, that the means of the PT distributions stands in the roughly the ratio of the sizes of the 2 targets. So in this case, you have the lead nucleus. In this case, you have the single nucleon. So, and then we can study coherent J-psi and perform more measurements. So, for example, angular distributions, the rapidity distributions, the PT square distribution, and the energy dependence. So, starting from the angular distributions, why it is interesting. So, in the case of UPCs, you have something called quasi-real photons. It means that these photons are as close as possible to a real photon. And so then it conserves the quantum number of the photons in vacuum, and this means that the vector meson in the final state will feature some kind of particular polarization, so it will be polarized. And the measurement is complicated, but in the end, it's you just take the J-psi, you go to the rest frame, and you look at the angular distribution of the positive muon in the rest frame. So it's very easy. Spoiler, it took me 6 years to publish this paper, and the paper is not out. We just reply to the journal now, so it's going to take a bit while longer. And this is very complicated, but then you can simply look at the plot here, and it shows you that there is an upward parabolic shape. Because in fact, if you study the polarization, then this is essentially the formula. It's 1 plus lambda theta square cos theta square dependence in cos theta, and this is the signature of polarization for the vector meson in the final state. Basically confirming the scenario of photo production physics. Then you can study coherent J-psi in terms of the rapidity, which, as I was saying in the beginning, is kind of, it's very similar at least to the direction of the vector meson in terms as far as is measured by ALICE. So these are our data, and these are our models. There are quite a few models. And we normally compare with this dashed line, this one here, which is called impulse approximation. So the impulse approximation is a computation, is a model which doesn't feature nuclear effects. So the fact that the data are so different compared to a model with the no-nuclear effects means that there are shocking nuclear effects to be considered from the data. And this is something that is called, if you do the square root of the cross-section in data divided by the impulse approximation model, so the square root of the ratio between the data and this curve here. This is something that we refer to as a nuclear suppression factor, which is very similar, very close to the nuclear gluon shadowing, if you want. It's if you want to be precise, we will call this the readily available, observable to the experimentalist, while the nuclear shadowing is something more for the theorist to make. And you see here there are a few numbers. So since, as you remember, they were saying that the rapidity of the vector meson relates to the Bjorken-x of the process, it turns out that at mid-rapidity, so in the central barrel of the detector, we are mostly probing 10 to the minus 3. And for rapidity, we have a mixture of 10 to the minus 2 and 10 to the minus 5. But you see that most of it is 10 to the minus 2. Using the energy dependence technique I will be talking about in a few minutes, we also access this part here, this remaining 5%, which is the most interesting part, because everyone can measure at 10 to the minus 2, but not so many can do 10 to the minus 5. Yes, so here I put an example that what we do in ALICE makes sense, that it really impacts life on this planet. So here is a paper from Gudzei, Christian, Strickman, and Zalov. Evgeny is actually the author of this beginning measurement here, so he definitely knows his stuff. They took our ALICE data and also took the LSCB data, so our competitors, and they used them to reweight the known, essentially EPPS 16 PDFs. And you see the effects from not using the ALICE data and using the ALICE data. So essentially it lowers a lot the uncertainties. Then we can study coherent GSI in terms of PT square. And sorry, just wanted to check, I'm still online. Sometimes it happens that you still talk and
Sorry?
So you can still hear me. Okay, fantastic. It's
Yes. I'm paying a lot of attention. Yes.
Okay. Other questions from the students? It's just in case.
No questions so far, but we can ask them. Alguém tem alguma pergunta?
I have one about the polarization JPC.
Yes.
I just lost something here. The polarization come from waving function, or have something in the process that polarized JPSI?
Yeah. So the fact is that you have that the photon interacts with the pomeron and results in a JPSI. These photons are almost real. These are as close as possible to a real photon. So the photon, as you know, has a polarization. Okay, so it means so essentially, since it is interacting with the pomeron, there are large chances that the polarization from the photon, which is known, is passed to the JSI. So this is the entire thought. So then we measure the polarization of the JSI, and it turns out it is transversely polarized. So this is about 100 about, which is the polarization of the original photon. And so we're all happy, the theory holds, and everything makes sense essentially for us in these circumstances.
Okay, thank you.
Well, if it's not clear, you can send me a mail afterwards. It's I will try to explain a bit better even. Yeah, so then I will go on with talking about the T-dependence. So this is where things look more similar to the diffractive waves that you saw during your undergrad studies, if you want. So essentially, we take our data, we split them in bins of T, which, as I was saying, is essentially the deviation of the nucleus in the original diagram, if you want. To be more precise, is the momentum transferred to the target. Essentially, it's for us, it's just an operation of moving from PT square bins to T bins instead. So this is just a technicality, but essentially we take our data here and we compare them against the model, because this is all what experimentalists can do. It's we take models from the theorist, we compare them to our data and say, aha, the theorist was right or wrong. So in this case, what we see is that the data, which are these points here, compare nicely with these models, whereas this model, which is Starlight, is not able to describe both the normalization and the slope of the data. So essentially, these models here contain nuclear effects like nuclear shadowing and gluon saturation, whereas Starlight contains neither. So in this case, then we say that the models, including QCD dynamical effects, are favored. And I will be showing you in 2 slides a better plot, essentially, which shows a few extra features that I will explain. But essentially, coherent site dependence, which goes from about 0 to 0.1, is sensitive to the average spatial distribution of gluons. Why I was mentioning here T of this range, because then if we go to incoherent site dependence, we jump again to 1, so much larger. The reason is because the size of the target is much different. So in this case, in coherent GSI, you are impinging a single nucleon instead of the entire nucleus, and this results in a much larger T. And then we have that the slope of the data is described by this purple line and by this green line here, whereas these models, they do this blue and yellow line, they do a very poor job. The difference is that these models contain dissociation, whereas these two, yellow and blue, they don't. Essentially, the main point is that incoherent site dependence is sensitive to the variance of the spatial distribution. And then we take all our points together and we plot them, and this is how the entire picture essentially what it looks like. So essentially, the ALICE data cover 3 orders of magnitude in T with here-like accuracy. This is our publicity stunt in ALICE to be able to justify all the measurements in T. But you see that it was a pity that with our data during run 2, we couldn't go any further in the measurement of coherent dependence. If we had just made exactly 1 single beam in addition to that, then we would have been able to see the full diffractive dip. So essentially, you see here, this really looks like diffraction in wave theory, if you want. Then we go to the most complicated of the few measurements, which is the energy measurement of the coherent of the photonuclear cross-section for the coherent GSI. And this is a bit complicated as a topic, so I'll try to make it simpler by starting again from the beginning of the seminar. So essentially, when we have vector meson photoproduction, so this type of process from UPC, you have the photon interacts with the pomeron, and then you have the vector meson. And in this case, the vector meson is produced in the same direction as the photon emitter. So I have that the lead nucleus goes in this way, the vector meson goes in this way. and so the photon interacts with this. But then you also have that the lead ion goes this way towards the left, but the vector meson is still produced on the right. Why I'm saying on the right, on the left? Because unfortunately, ALICE only has a muon spectrometer on one side only. So for us, we can only measure the vector meson on the right side of the detector, not on the left side. Pity. But the cross-section is a sum of the two diagrams. So in one case, so when the vector meson is produced in the same direction as the photon emitter, you have a low energy photon, which means that you are probing a high X gluon. In the other case, you have a high energy photon, which interacts with a low X gluon. And you see here the difference between the two. And so you have a contribution of both. So then you cannot access this part here normally. This photonuclear cross-section sigma gamma lead. You cannot normally access it because you have the sum of the two. So there are a few ways to do that. So you know that most of the photon flux is at low energy. It makes sense. It's much more difficult to generate a high energy photon. So then it means that if you just stay in the regime of low energy, then you can get the photonuclear cross-section. This is a bit of philosophy for the game here. So when you study at mid rapidity, first you have that mid rapidity y is a 0. So then these two sum up together because they're the same photon flux. And in this case, the UPC cross-section, so the measured cross-section here, is directly linked to the photonuclear cross-section. In the other case, at 4 rapidity, you have that 95% of the cross-section originates from the low energy photon. So then approximately the UPC cross-section is the photon flux times the photonuclear cross-section. But you still want to get the 5% left from the high energy photon. So this is a bit the interesting part. There are two ways to disentangle the nuclei. One is through neutron emission, so which is the measurement that is here. Essentially, you have that you have the main diagram that we've seen a few times now. So you have photon, lead ion, and the J side. But these two nuclei, they're still very close to each other. So then they can exchange additional photons, and this may result in the excitation of a neutron. And so then you can measure neutrons in ALICE. But this is also why I was saying in the beginning that UPC physics is the most reasonable type of physics in ALICE, because essentially you can imagine that exchanging photons is much easier the more these two lead ions they're close to each other. So this means that we're actually doing a measurement of the impact parameter of the collision. And essentially, we simply check the neutrons. So if we have no neutrons, or if we have neutrons in ALICE, and this means that you're looking exactly at two different kinds of impact parameter. It's also quite interesting to see that here is essentially the start of UPC physics. So twice the radius of the nucleus, which is the 14 Fermi, so 2 7. And that you can still have UPCs, and actually it's more incredible to have UPCs even at 1,000 Fermi of distance between the two lead nuclei. This is something that is awesome, in my opinion. It's, that you can still have UPC events even when the two are so far away from each other. And the other technique is to go to peripheral photoproduction instead. So instead of being farther away from each other, they get very close, so they do overlap. And so you study coherent photoproduction in this case, and you study coherent photoproduction in UPC case. You put them to system, so you have a system of equations that high school students could solve in principle. And you can extract the photonuclear cross-sections here. So it's a very, very, very easy. And the result of all of this is that Guillermo Contreras here he took the round 1 data by ALICE and measured essentially and did this type of discrimination of the two solutions for a positive and a negative photon flux. And you see these results. I'm going to accelerate a bit because I think it's about almost time for the end of the seminar, unfortunately. Instead, here this is the neutron emission results, and compared with these points here, which are the peripheral results from before, and you see that the picture is very much more complete using neutron emission because we have more events and the measurement is more solid, and we could do a better assessment of the uncertainties. And you see, first of all, that there is agreement between the two techniques because essentially they are the same technique in disguise. That we managed to extend by about 300 GeV the reach, also having quite a few points. We also see that CMS published afterwards the same data, the same results, and they managed to cover perfectly the gaps that we left in ALICE, so they did our remaining homework for us instead. And that we also managed to measure the nuclear suppression factor, which is again a proxy for the nuclear gluon shadowing, if you want. And you see here that this is about 0.5. And if you remember the beginning where we had these huge uncertainties at a very low Bjorken-x of 10 to the minus 5, it was something that looked like this with a very large band here. This is something that really helps in reducing the uncertainties for nuclear shadowing. Yes, so yeah, I was putting some more material, but I think you are really confused enough. Just to say that different particles are more sensitive to saturation effects than the others. So JSI is the one that is the least sensitive among the three of them. Raw is very sensitive. You see here the difference between saturation and non-saturation, but unfortunately it suffers from other problems. So phi will be the perfect particle for us, but the phi is very tough to measure, unfortunately. It's and just a hint of what we want to do in run 3 and run 4, because I'm not sure if you know, but in ALICE we are in something called, at LSE we started almost 2 years ago run 3. So ALICE is confirmed until run 4, and then we might have an ALICE 3 for run 5. And the main game is that we will have more data. This is the main idea. So essentially, if any of you is interested in hardware, if we think about ALICE, ALICE was a trigger detector in run 1 and run 2. Now we have something called continuous readouts. So essentially, we have a continuous stream of data coming out of the detector. And for UPCs, essentially, we want to study the cross-section for a few of these particles here, all the germanium states and some bothonium as well. So in this case, the upsilon 1s is a prime target, although it will be very hard work for us postdocs to manage, I think. Yeah, I think this is kind of all, I guess, I could say. If you want just an extra word is that this is not the end of UPC physics. UPC physics is much more than that. We can study tetraquarks, for example, pentaquark for the production. This is tetraquark production through photon-photon fusion. This is the goal is to check the production mechanism of tetraquarks. You know that there is all this conundrum of molecular and true tetraquark shapes. And by checking the cross-section of the tetraquark in photon-photon fusion, we are basically accessing the wave function of the tetraquark, and this reflects to the nature of the tetraquark itself. If it's loosely bound, if it's more bound. Then we can study light by light scattering, so essentially photon-photon and photon-photon, because this relates to axions searches, so essentially looking for dark matter candidates. So yeah, there's quite a lot to do. It's not so many people that are available for that. So if you want to be part of UPC program in ALICE, let us know. And there is more than enough work for pretty much everyone. It's okay. This was all I had to say. Yeah.
Okay, thank you very much for the interesting talk. Let's see how many questions we have. So, se vocês tiverem perguntas, pode perguntar, por favor. So we have one question on the chat. Does ALICE have any future proposals on the schedule for measurements of the effective cross-section in double particle scattering?
No, it's no. I don't. I think it's so. Wait, let me check again. Does ALICE have any future proposals? No, I don't think so. It's well, to be honest, at the moment we have enough problems trying to make sense of the data that we currently have. It's maybe for the future, but I don't know. Sorry.
Yes, I think he asked about double particle scattering in central collisions, but we have some work on double particle scattering on UPCs, right? You kind of have that when you have this neutron production that you detect in the 0-degree calorimeter. So have you thought about it?
Double parton scattering? You mean two pomerons?
Well, you presented mostly exclusive or dissociative production of J-psi, but maybe inelastic production of J-psi, but you start with a photon. Well, if you're going to produce two J-psis, starting with the two photons, right, from one side, and getting two gluons from the other side.
This is what you mean, okay. It's no, because I wasn't sure if you meant two pomeron processes or one pomeron with the photon. So the point is that to have two photons, it means that the cross section is, it's you have twice the coupling of the electromagnetic coupling, so it gets very tough to measure the cross section. So you need a lot of data. So checking double photon production, this is the actual term that we use for that, is in our plans, but I find it tough to believe that we can do that easily. Instead, I was thinking that you meant originally two pomeron processes. That's a different type of physics. This is called the central exclusive production. So you see an example here when you generate two J-psis in a single event. And essentially the point is that you have as called two pomerons interacting with each other, and this can create two J-psis in a single event. But this is not a fully induced process. This is pure derivative, if you want.
Okay, thank you. More questions?
So I have one. When you showed us the coherent data, the comparison between the impulse approximation and the predictions that basically got the data, we had this suppression factor, right? So
yes.
the coherent data, we kind of see the need of this suppression factor. And about the incoherent case, what kind of nuclear effect is more expected to, have a great effect? Is it also the shadowing or something? What else can be there?
Well, you see it a bit here if you want. It's well, here there is a shadowing involved in all these models, so definitely the impact of shadowing is there as well. But yeah, I think that's the end of it for now, because the main part is that here there is already the effect, as we think of it, not of saturation, but of something we call hotspots, if you want. So these are, well, the accepted term is subnucleonic degrees of freedom. So essentially, there is extra stuff inside of really hotspots inside of the nucleon, if you want. So I think there is a combination of both. For complete saturation effects, we have to wait for an energy scan, if you want, of this cross-sectioning team. It's does this answer your question fully?
Yeah, no, yes. So maybe fluctuations would enhance our understanding.
Yes, you see here the effects, the difference between the two. So in one case, this is without subnucleonic degree of freedom, and this is with. So essentially, it's increasing towards larger T's. Sorry, I was under the impression that the students were more like master students, so I was not expecting. Maybe I should have raised the target of the talk. Not.
No, it's okay. It's fine. It's very interesting talk indeed. More questions?
Yes, I have 2 questions. If you can talk again about the polarization, I don't know if you can explain a little bit more about the elastic dependence in the equation of the wave function of photon. For example, okay, real photon, we have a transversal polarization, just. Yes. But when you talk the J-psi polarization, you include some gamma 5 in the waving function of photon or not? To select the chirality in the process, something like that. This is something that I'm thinking.
Yeah, so you're a theorist, right? It's
because sometimes I think about the future polarization colliders, and I'm have a little bit difficult to understand how we have the J-psi polarization when you not have beam polarization.
that is what. Okay. So let me go back here. So this is the entirety that ALICE sees. So you have the lead, the photon, the pomeron, and well, it doesn't see the pomeron and it doesn't see the photon, but it sees the lead ions and the vector meson. Okay. So you agree that the photon is almost real, right? Well, at least you trust me in saying that. It's okay.
Okay, you're right.
So it's this diagram here. You have this one is almost real, so it has its own polarization. Then you have a pomeron here, and then you have the vector meson here. So there is something called S-channel helicity conservation hypothesis, which is really an hypothesis, is the fact that the pomeron doesn't affect the transmission of the polarization from the quark to the diquark here, and then to the vector meson in the final state. Okay, so then essentially the measurement of the polarization of the vector meson in the final state is a test to see if S-channel elasticity conservation holds in here, which is not very clear because this is actually not an S-channel in principle type of event. Okay, so then you take the vector meson. If the S-channel elasticity conservation hypothesis holds, it means that the vector meson will have the same polarization as the photon, which is not a polarization it gets from the beam. It's a polarization that it receives simply because the photon is almost real. Okay. And then it turns out, sorry?
Okay, perfectly. And I understood.
Okay. It's a bit subtle here because also I hate the fact about this channel elasticity conservation, but it is written on the paper, so it's at least we didn't cheat them.
Okay, sometimes I think all time when you have a UPC, ultra-peripheral collision, almost we have quasi-real photons from Isaac-William radiation. And so almost we will have JPC polarization, or just when happens something different to take JPC polarization, polarized.
Sorry, I didn't hear you.
Sorry. No, my question is, almost we have quasi-real photons, so we have transversal wave functions, but we can select the final state that we have some JPC not polarized and JPC unpolarized. You can measure this difference, not?
You're saying if you can select the different polarizations for the vector meson, is that what your question?
Yes, because almost we have a transversal polarization from photon, but
yes.
But
that's
in the final, yes.
It does, because you see it doesn't really so it transmits fully the polarization to the vector meson in the final state. I think so. You are a PhD student, I guess, or in theory, something like that. So I think that here you are confused about Q square. So there are two types of processes that normally you can find this type of events. One is called the photoproduction, which is this type of mechanism. So essentially it means that the lead ions are lost along the beam. And in this type of case, it means that the Q squared, the moment of transfer from the photon, is very, very small. So it's not enough to change essentially the direction of the lead ion. And the other case is called electroproduction, which was the process that you saw, for example, at HERA. At HERA, they can measure electroproduction. What does it mean? It means that they could measure. So since HERA was an electron-proton collider, they could measure the deviation of the electron. So then essentially they have the electron beam, and then they see the scattered electron inside of the detector. And this means that they had a leverage on the Q square of the process, so they could measure electroproduction. In this case, the photon is not real, and in this case, the ratio of the longitudinal to transversally polarized part of the cross section has a trend and it features more. It has a trend with the Q square, and essentially it drops to 0. Sorry, it's that way. Sigma T over sigma L drops to 0. Most of it becomes longitudinal polarization, if you want. But this is something that you select with the Q-square. This is actually something that I didn't say, but it is here in these slides, because when I was doing this plot here, so Zeus, for example, I never could find the photo production for Zeus. For H1 I did, and in fact you see ALICE and H1, they both measure photo production, and in fact they do agree with each other, while Zeus instead strongly disagrees. And the reason is because in this case the Q-square beam is not 0 like here, but it is from 2GV squared upwards. So this is electroproduction, and this is essentially already, it gives you an idea of the fact that something will change in the ratio of the cross-section between longitudinal and the transverse polarization as a function of Q-square.
Thank you a lot. Thank you a lot. I understand much better.
Okay. Well, I think that's enough. Let us thank again Simone for giving us this interesting talk. And then please, the students, remember to sign the link that Edgar put on the chat. Então, vocês lembram de assinar a lista de presença que está ali no bate-papo. So, yes, that's it. Thank you very much.
No problem. It's a thanks for the invitation. I forgot to say. Yeah. Thanks a lot. Bye-bye.